to address is first I want to put P to be off shell, meaning that P squared is not equal to M squared. Let me just first do this. Okay, the reason is very simple. It's because if P squared is equal to M squared, then this is on shell particles, right? If these are on shell particles, when you're discussing the S matrix, there is no 2-point S matrix. 我们在讲 S matrix 的时候，你没有两个的 S matrix， 对不对？你一个 state 跟一个 state 就是 either overlap 或是 orthogonal， 对不对？第一个 S matrix non-trivial S matrix 是什么？是不是一个 decay 的 S matrix， 一个进来然后 decay 出去，这是 1 to 2的嘛，对不对？所以换言之，如果说 P square 等于 M square 的话，这个 object 并不是一个 physical observable。对，所以换言之，我要 compute 它，我现在要 compute 这东西，但是我要 compute 它唯一存在的方式是一个 non-physical observable 的方式存在。那你们会问我说我干嘛 care？ 那如果是 non-physical observable 的时候，我干嘛管它？为什么我要做这个计算？这很简单了，因为如果说我今天 consider 假设一个这个也是一样 phi cube theory， 我 consider 这个 interaction 的话，4点的 interaction， 在 phi cube theory 4点的 interaction tree level 是不是有两个进来，透过一个 propagate 出去嘛？对不对？大家同意吗？对不对 ？Good。那如果在 one loop， 我是不是就可以直接加上这个 diagram？ 对不对？在 one loop level 的时候，我就会有这个 diagram 进来的，对不对？所以我可以直接把这个东西的结果直接带进来，这是我为什么要算这个东西，对不对？我只要把这算完，我只要把这样，我就可以把它带进来就可以了。OK， 而且这样子的情况下，我是不是很容易就可以去算 multi loop 的 correction？ 对，我一旦算完这个之后，你 multi loop 的 correction 值再继续加下去。对，就每个值一直不断在塞这个家伙，所以我把这个家伙拔出来去算它，算完之后就可以真的放进我的 physical observable 里面。那它在 physical observable 里面出现的时候，它的这个 momentum P 是不是当然不会 on shell？ 对不对？它是中间的 momentum， 它并不是 external state 的 momentum， 所以它并不会 on shell， 所以它 P square 当然就不应该等于 M square。OK， 这是为什么我要做 P square 不等于 M square 的计算。OK，so I just want to compute this graph, but the important thing is that my external momentum, I'm setting P squared not equal to M squared so that it's not on shell. And why is that? Well, there's really one reason, but it's split into two steps. The first step is that actually this 2-point function is actually not a physical observable. Okay, because these are momentum eigenstates. So if P squared equals to M squared, that means that this is an on-shell single particle state. But there's no S matrix for on-shell single particle state when there's just one particle to another particle. This is not an S matrix. The first non-trivial S matrix is a decay S matrix, which is one particle decaying into two particles. Of course, there's two particle, 3 particle, but the minimal is 2 particle to a particle. Okay, so if this is on shell, this is not physical observable. So if you want a physical observable for a phi cube theory, you will have to consider things like this, a 4-point interaction. But then this graph will be useful because then you can compute the one loop correction, which looks like this, and you can just get whatever you computed here and just stick it in here. And that'll give the correction to your physical observable. Except for that, again, so this P here comes from the sum of the momentum here. So even though this P squared is equal to M squared, this P squared is equal to M squared, this is the sum of these two P, then this is obviously not going to be, it's not going to square into M squared. It's just that simple. Okay, so we're going to use this, but we're going to do P squared is not equal to M squared. Okay, so let's just do the computation. So here the answer is going to be just this graph. The answer is just going to be 1/2 I lambda squared because there's two vertex, so there's here lambda. And so we're going to do this integral again. Oh, by the way, 你们有谁做上次我给你们作业吗？有做出来的？你们知道有作业吗？知道哈 ，OK。我当然那个就是我劝你们尽量试着去做做看 ，OK。我什么时候？我希望至少下个礼拜有一个人能做出来 ，OK。你试着做做看 ，OK。Again， 我现在都会做这些积分，所以这些积分用到的东西都是你们在作业里面会用到的方式。All right. pi d is very simple. 1 L minus P squared minus M squared, and then L squared minus M squared. Okay, so this is the integral we need to do. Okay. All right, good. So let's do a step by step. So first is minus 1/2 lambda squared. Again, we want to put this in. We want to use Feynman parameterization to put this into a common denominator, right? So that means that we have this gamma 2. Sometimes I use D. Okay, and we use Feynman parameterization, meaning that we introduce the Feynman parameters, alpha 1, alpha 2. Each one is from 0 to 1, delta 1 minus alpha 1 minus alpha 2. The reason that you can do this, we already proved last time. Okay, the identity that I'm using here are all just the identities that I talked about last time. So here, then we have alpha 1, L minus P squared minus M squared. There's too many parentheses. I don't know. Maybe this will be it. Plus alpha 2 L squared minus M squared. And then this is 2. Okay, that means just Feynman parameterization, right? When you have 1 over AB, this becomes integrate alpha 1, alpha 2, delta 1 minus alpha 1, alpha 2, A alpha 1 plus alpha 2 to the second power. Again, you don't need to actually write this down, I mean, because it's going to be recorded. But, okay. So since alpha 1 plus alpha 2 is M squared, is equal to 1, so we can actually simplify this denominator a little bit. Let me just use a different color. Okay, so obviously there's going to be L squared times alpha 1 and L squared times alpha 2, right? So this thing here, alpha 1 plus alpha 2 is 1, so this just gives you L squared. It's the same thing with M squared, minus alpha 2 M squared and minus alpha 1 M squared. So this is going to give you minus M squared to N. And then in the middle, there's going to be minus 2 L dot P alpha 1, and then plus alpha 1 P squared. Okay? And you know what we want to do, right? We want to make this a complete square in terms of L. Right? Okay? So that means that we want to rewrite this as L minus alpha 1 P to the square plus or minus alpha 1 square plus alpha 1 P square minus M square. Okay, but this is just alpha 1 for alpha 1, this is just alpha 1, 1 minus alpha 1. But 1 minus alpha 1 is really alpha 2. So this piece here, I think you just write it in a more symmetric form. It's just alpha 1 times alpha 2 p squared. Doesn't matter what I write. Okay, so then the bottom is really like this. So the reason that I want to write it like this is because then I can just rewrite this as, just define this as my new L, right? So that means the integral that I'm integrating becomes much simpler. So this is just going to be minus lambda squared to gamma to integral dl prime to d 2 pi d. And then this is my L prime now. This is L prime. Okay, so this is just L prime squared plus alpha 1, alpha 2 p squared minus m squared. So now it's just this to the second power. And then from now on, I'm just going to call, because I don't want to write this infinite number of times. So I'm just going to call this integral f alpha 2. Let me just call this f2. f2, and of course fn will be defined as integral pi I equals to 1 to n d alpha I, and then delta 1 minus some I equals to 1 to n alpha I. Okay, because we're going to do a lot of these integrals in the future, so I don't want to keep writing this out every time. Okay, so the Feynman is f because I just call it for Feynman. Okay, so it's just, I'm just combining all the Feynman crap thing into here. Okay, good. So then I can just write f2 here because it's just the Feynman crap thing. It's just some integral over alpha that only contains alpha stuff. Everybody okay with that? Okay, cool. Good. So now we can just do this integral, right? Because we know how to do this integral very easily, right? Because this is just L prime squared. There's no direction in terms of L, right? Even though L is a vector, but it's appearing in your integral only as L squared. So this is a simple integral to do, right? And we discussed how to do this integral last time. So if you don't remember, let me write it here. So whenever you have dl to the d 2 pi, you should really try to prove this. L squared, let's say you have some L squared upstairs and then some L squared downstairs minus some delta. And this is some A. And the answer is 4 pi d over 2. We derived this last time, gamma A, gamma d over 2, gamma A minus B minus d over 2, and gamma B plus d over 2. And then you have delta A minus B minus d over 2. Okay, so this is the formula that we have. So whenever you have that vector integral, it becomes even though L is a vector, but because whenever it appears in your integrand just as L squared, then the integrand is straightforward to do. Okay, we can just integrate with that. But once you integrate once, you can just write down the general formula. Okay, good. So we can just plug this into here. Okay, so A is 2, B is 0. Okay, so that means that this crap here is just minus lambda squared over 2. Now there's a gamma 2 here, but of course since A is 2, there's also a gamma 2 here. So the gamma 2's are going to cancel out. And since B is 0, because there's nothing like L squared on top, so that means this is 0, so this is gamma d over 2 is going to cancel the gamma d over 2 as well. So that means that this whole thing over here is just gamma, just A equals 1 minus d over 2. Did I get 1 minus d over 2? Oh, sorry, A is 2. 2 minus d over 2. Yeah, A is 2, right? A is 2 here. Good. A minus d over 2. And we got, of course, we have 4 pi d over 2. And it's very simple. Then you just have f2 times this delta thing here. So the delta is alpha 1, alpha 2 p squared minus n squared. Or so this is this n squared minus alpha 1 minus alpha 2 p squared. And this is to the order d over 2 minus 2. 我写到这边有没有问题？这样有问题吗？我在做这积分而已。Okay, just nothing fancy about this. Good. 那我们现在我们知道嘛，这个 d 如果是四维的话 we know that when d equals 4, this is just 2 minus 2, which is 0. Right, so we know that gamma function has poles at 0 and negative integer. Right, so this, again, you find that this is a divergent integral. Okay, so that means that when you're computing the one loop correction to this propagator, you're getting a divergence again. Okay, so so you're getting this divergence, but now you know what to do, right? Just put d equals 4 minus 2 epsilon. Alright, so we use dimensional regularization again. Set d equals 4 minus 2 epsilon. And all this crap here, a leading order just becomes lambda squared over 2 gamma epsilon 4 pi d over 2. And then F2 integrating over m squared minus alpha 1, alpha 2 p squared. And this is just epsilon. Oh, sorry, minus epsilon. Okay? Good. So now we can look at the result. So let me just recollect everything. So this answer here is just 4 pi squared leading order. So now we can expand gamma in terms of 1 over epsilon. There's a 1 over epsilon piece from the gamma plus the epsilon that is coming from here. So this is, sorry, this lambda squared and minus, and there's a 2 here. And then there's a minus log again. Alpha 1, alpha, sorry, m squared times alpha 1, alpha 2, p squared. You have this log thing again. And then you have f2. Okay, where f2 means that you have to do the integral. You have to do this integral here. I should mention that you have some constant here. You should have some constant. Everybody see what's going on? 你都看到发生什么事吗？这 gamma epsilon 是不是会产出 1 over epsilon？gamma epsilon 是不是等于 1 over epsilon 再加上某个常数 constant？ 我先不太管这个 constant， 你们马上就知道为什么我不太管它。但是我先它是加一个 constant， 对不对？把它来做级数展开嘛。但是它有这 1 over epsilon 的 piece， 那一旦有这 1 over epsilon 的 piece， 其他这种 epsilon 都会因为有这 1 over epsilon 载下来变成 log。对不对？因为 again， 如果你们不记得的话，因为这个东西是可以把它写成 full epsilon log m squared 减掉 alpha 1 alpha 2 p squared， 然后再用小展开，是不是等于1减掉 epsilon log 点点点点点这样子？所以你有 1 over epsilon 的东西，你就 pick out 这个 log 的东西。大家同意吗 ？OK， 所以任何时候你有 1 over epsilon， 你就会有 log。所以 log 的这些这个 running 事实上是来自于说，从场论的计算的角度来讲，是从这 1 over epsilon 来的。你有任何时候你有这些 divergence， 你会出现这些 log 的 piece。OK， 但是这是从场论的计算的方式来讲的话是这样。那我们上次有讨论过嘛，对不对？我们上次讨论过是这 1 over epsilon 明明就最后就 cancel 掉。对不对？在实际 physical observable， 那为什么会有 log？ 所以 obviously 这算是这种计算的方式跟你讲说它会有 log 的出现，可是这不应该是最终的答案嘛？那上次我们有看到，就是我们如果你有 unitary 的话，你可以看出它一定要有 log 在那个地方，这是我们上次讨论的，那是物理的解释。OK， 但是如果说就计算的方式的话，那这 log 的出现是因为你有这个 1 over epsilon。OK，alright， 所以你先有这个1 over epsilon 的出现。然后我们现在得到这个 log， 我们还没做完了，因为这 f2 的 integral 还要再做积分嘛。对，我们还有这 f2 的积分。But f2 的积分基本上不会有太多的变化 ，OK， 因为不会有太大的影响，不是变化就是太 dramatic 的事情，比如说又产生一些 divergence， 不会，因为你可以看得出来说，这 alpha 1 alpha 2是0、1之间嘛，对不对？那在0、1之间的时候，这些东西都没有任何发散的东西嘛，对不对？我 1 over epsilon 只是个数字嘛，它本身就已经发散了。那这个东西的话 ，alpha 1 alpha 2在0跟1之间的时候，就顶多只是 either 是 p squared 等于0，对不对？就是 either 这一项有或是没有的差别，并不会发生什么 dramatic 的东西，对不对？同样的，你这个，我这只是 constant， 当然不会。好了，为什么我不 care 这个 constant？ 因为很简单，我虽然把它写成这样，可你们知道 ，again 我们也有一样的问题嘛，对不对？不算是问题啊，但是因为我们都已经知道怎么做，就是这里面有是 m squared。可是我们知道 log 里面不应该有 m squared， 不应该有量纲嘛，对不 对不对 ？log 里面是个指数嘛，我也不知道是不是指数，我不知道中文名字是什么。但是它 log 里面那个 argument 不应该是有量纲的嘛，对不对？所以你今天出现 m square p square 的时候，我们应该要放一个 lambda square 来 cancel 它的量纲，对不对？我 lambda square 是大于 mass 的，对吧？可是说 lambda 是什么，你也不知道 lambda 是什么，对，这是我们随便塞进去去处理量纲的嘛。我们当然会再给一个稍微比较好一点点说 lambda 是什么的 prescription， 但是我们现在就先塞一个 lambda，它是弥补量纲。那我们上次也做过这件事情嘛，我们就也是放了一个 lambda 在那边。那你们刚刚也看到说那 lambda 发生什么事，它最后都 cancel 掉了，对不对？所以 lambda 是什么东西基本上不重要，对不对？那 lambda 是什么东西不重要，是代表这个 constant 是什么东西就不重要，因为任何的 c 都可以吸收到这个 lambda 里面嘛。大家同意吗？对，我今天只要把 lambda 对变成什么 a lambda 的话，我是会多出一个 log a。对吧？有会讲，所以说这个常数是什么完全不重要，这是 completely irrelevant，所以我就根本懒得去写它。OK， 这事实上也是有这个会有也是为什么说，因为你其实那个如果你们真的有在 follow 的话，你们跟得上的话，你会发现说，其实我不应该只有这样子，因为比如说我这边是4派 d over 2，那 d 如果是4减2 epsilon 的话，这边是4派的2次方减2 epsilon， 4派2减 epsilon， 对不对？那既然4派2减 epsilon 再乘上这个伽马的话，这伽马有1 over epsilon， 这边是就应该有个 log 4派，对不对？因为它也有个 epsilon 在这个地方嘛，所以它也同样能够展出一个 log 4派嘛，对不对？那 log 4派也只是一个常数，所以我就丢在这个常数里头，懒得管它。所以任何的常数在这个里面对应的都不是很重要的，因为 again 你这常数会是多少也不重要，因为这常数会影响到时候你去 fit data 的时候 fit 的那个 lambda 会是多少，然后再做真正的 prediction 时候又会都相消掉，所以这是 irrelevant 的东西。OK， 有点像是重力位能的，你说说重力位能没有绝对值嘛，对不对？就只有相对应才有意义嘛，对，是一样的道理。OK， 这些常数是什么是很重要。OK， 当然，可是我们还是会希望说能够把这 integral 做出来。所以假设说我现在这 integral 你可以实际上去做，在 arbitrary m square 的时候，其实会稍微有点复杂，它的 closed form 会有点复杂。但是当你的 limit， 当你的 mass 很小的时候，当你的 limit m square 趋近于0的时候，这个 integral 就很好做。OK， 你的答案就是我说 integral 是什么？是这个 alpha 1 alpha 2 p square 跟 f2 是这个 integral。你在这 f2 的话，你可以直接把 alpha 2换成1减 alpha 1，然后去做这个积分，这积分很容易做。所以 in the limit of 这样子的情况下，你的答案就很简单，就是等于负 lambda square 1 over epsilon 减掉，sorry 1 over epsilon 对，加2减掉 log p square over lambda square。OK， 就是当你 m square 趋近0的时候，你就得到这个答案。OK， 好，这样可以吗 ？Good。所以我们现在又可以玩一样的游戏嘛，对不对？我们现在又要把这个东西，我们先算完这个东西，我们是要把它 fit experimental data， 对不对？因为我们现在一样，我们跟刚刚一模一样有一样的效应嘛。我们有个很奇怪的1 over epsilon 的 UV divergence， 对不对？然后我们又有这个 log p square with 这个 lambda square which we don't know what the lambda square is except that it's there to cancel the dimension， 对吧？So in order to remove these things, what we need to do is we need to try to fit this to experimental data， 对不对？我们刚刚就讲过，这个 2-point function 并不是一个 observable 嘛，所以你没有实验 data 可以去 fit， 对不对？可是我们是说我们要拿这个 2-point function， 我们是不是要把它塞进这个里面？所以我们就得到这边。We have this 2-point function, even though it's not a physical observable, but we can fit into an experiment where we scatter 4 particles, 2 particles incoming and scattered out, 2 particles coming out, right? Then, so we can again compare it to the measurement of this, like this process, which is given now by sum of this process plus at some order to this process, and then we can put this into here, right? Okay, so let's do that. Let me just let it make a safe space. And let's do that. Let's try to fit it into this. Oh, sorry, this is. So let's just call the momentum coming here. This is P. This is P. This is P. For obvious reason, because this P will then now become this P up here. Okay? Good. So we can write down what the answer is. So for this guy, because there's two interacting vertex here, so we know that the theory prediction gives you gives you I lambda squared I P squared. This is for this guy. For this guy over here. Okay, it's just the two interacting vertex plus the propagator, right? So very straightforward. Good. So then we can have this guy. There's also two interacting vertexes. Again, you have I lambda squared. But now you have two propagators on these sides. So there's I P squared. And then there's another I P squared. And then you just stick in whatever that thing is for here. Right? Or maybe not draw it, but actually write it down so you have more feeling. So just put that in here. So there's minus lambda squared. I'm going to remove this 2 as well, because this 2 is also just a constant, so I'm going to absorb this into here. So I'm going to forget about that graph, and then have this log P squared over lambda squared. Okay? Is everybody agree with this? Okay, so let's call this process as some m, a function of m p squared. Okay, so let's so we have lambda m p squared. Sorry, we have some process m p squared that involves this ultraviolet, this mu UV divergence that is sitting in here. So again, what do we want to do? We want to let it map to a physical observable, right? We just want to map to this experimental data. So we're going to do the same thing. We're just going to say, oh, this is equal to some lambda minus lambda squared tilde. Let me call it tilde. I'll just explain why tilde. Okay, so this again, this lambda tilde square r is the thing that we measure in the experiment. So we measure this. And again, we're going to do the same thing. We're just going to fit what lambda square is. OK， 所以我们要跟刚刚做一模一样的事情。好，那我在这边稍微停一下，我要说明一下为什么我稍微在这边做了一个记号 lambda tilde。因为这个 lambda tilde 事实上，因为你会发现说这个的 leading order， 因为在原来的这个，或者我在回到 Lagrangian 来讲好，我的这个 lambda 在 Lagrangian 里面的时候，是不是其实是带有 dimension？你们现在应该要很熟练说怎么 count 在一个 Lagrangian 里面的parameter 它的 dimension。这我们在上学期已经提过好几次了，我们这学期开始也有提过，其实上堂课有提过嘛，对不对？所以这个 lambda 跟刚才 lambda 5.4 是很不一样的东西。刚才 lambda 5.4 的那个 lambda 是 dimensionless 的嘛，对不对？但是这个 lambda 是 dimension4。那你们应该开始也知道，在 physics 里面，我们会习惯是用我们会去对上 dimensionless 的 parameter， 对不对 ？OK， 所以这是为什么我叫做 lambda tilde square， 因为它事实上是等于原来的，你可能原来的 lambda r， 如果你们一般所谓的原来 lambda r square 的话，还有它的这个东西，它的 scale， 它的 scale， 假设我今天是在 p square 等于 q square 的时候。这个我define叫 lambda r square， 因为这 q square 实际上这整个 combination 是 dimensionless。我刚才不用做这件事情，是因为我刚才的原来的 lambda 就已经是 dimensionless 的。但是在 dimension4 的时候，你